Hi, I am Santosh Parajuli from Department of Electrical and Electronics Engineering, School of Engineering, Kathmandu University. Welcome to the fifth lecture, Analysis of a MOS Field Effect Transistor, in the 5-part lecture series of the course Electronics Engineering. Let's analyze MOS transistor large and small signal behavior by finding all the branch currents, all the node potentials, and by drawing the small signal equivalent circuit around the operating point. The calculated voltages and currents should be verified by using software as well. The circuit has one nmos field effect transistor, a drain resistor, a gate resistor, a current source, and 2 batteries. Transistor threshold voltage is specified as 1.5 volts, K as 0.5 milliampere per volt square, and hourly voltage as 75 volts. K is device constant related with aspect ratio of MOSFET. Some basic concepts are needed to solve this nonlinear circuit, and these concepts can be generalized to solve any nonlinear circuits with MOS field effect transistor. A. There must be consistency in assuming the polarity of potential drop across an electronic device. B. One should always be aware of the fact that current through a resistor is not equal to voltage over resistance, but is always equal to voltage difference over resistance. C. Sum of entering currents at a node is always equal to sum of outgoing currents through that node. D. Irrespective of transistor operating region, source current is always equal to sum of gate and drain currents. This is simply Kirchhoff's current law. DC gate current in a MOS field effect transistor is 0, so source current is equal to drain current. E. To ensure active region operation of a NMOS transistor, drain potential should be highest, source potential should be lowest, and gate potential should be in between drain and source. F. The gate to source potential difference in a NMOS transistor should be positive, and in the active region it is given by under the root drain current over K plus threshold voltage. In a bipolar transistor, base emitter potential difference is nearly equal to 0.7 volts. G. Small signal equivalent circuit for NMOS transistor is same as that of PMOS type transistor and is shown in the circuit. The equivalent circuit has one resistor and one dependent current source. The input port is left open because gate current is 0. GM is a factor which relates output drain current with input gate source potential difference. RO arises due to channel length modulation effect and models the non-ideality of the dependent current source. The value of RO is hourly voltage over quiescent drain current. GM is given by 2 times drain current over VGS minus threshold voltage. GM and RO are the small signal parameters of a transistor, and they are always operating point dependent. To find all the branch currents and node potentials, let's start from the easiest. The source current is 0.5 milliampere. Because there is a current source sinking 0.5 milliampere current from source node to minus 10 volts battery. Drain current is also 0.5 milliampere. The drop across drain resistor RD is 0.5 times 15, that is 7.5 volts. The drain node potential is 10 volts minus 7.5 volts, which is 2.5 volts. After finding drain potential, let's find the gate potential. Since gate current is 0, gate is at 0 volt potential because drop across gate resistor is 0 volt. VGS is computed by plugging in ID as 0.5, K as 0.5, and VT as 1.5. The source potential is then found as minus 2.5 volts. The transistor is indeed in active region because drain node potential is 2.5 volts, gate node potential is 0 volt, and source node potential is minus 2.5 volts. Potential difference across the current source is higher potential minus lower potential which is minus 2.5 minus 10 volts, which equals 7.5 volts. RO is early voltage over drain current, 150 kilo ohms. GM is 2 times drain current over VGS minus threshold voltage, which is 1 milliampere per volt. Now let's verify the circuit using multisim and electronic simulation software.